what we have done so far is the version which is known as the Heisenberg's approach, which is essentially what we called matrix mechanics. And as one of the students in the forum also pointed out, it does become difficult after certain simple problems. And the other version we learnt about is the Schrodinger's approach, which is nothing but what I will call wave mechanics, and it considers particles as having associated waves and solves for the wave function. The 1D Schrodinger equation, and we have solved it in two cases, is written as minus h cross square over 2 m d2 psi over dx square plus Vx psi x equals E psi x, and I am going to put an n here as a subscript to show that these are the eigen functions which satisfy the boundary condition. So, the satisfaction of boundary condition gives you the eigen values, energies E n, and the corresponding eigen functions. So, this is the approach that we are going to now follow in the coming lectures and apply Schrodinger's equation to solve problems, some standard and some non-standard, where we are going to use numerical approach to solve the problem. We are going to start with very simple problems and slowly increase the difficulty level. So, from now on what we are concentrating on is the solution of, for the time being, one dimensional Schrodinger equation. And since I am starting with simple problems, I will start with something called the symmetric potentials. And what I mean by that is that if I go from positive x to negative x, the potential does not change. So, V x is V minus x. For example, if I take a potential which is simple harmonic, that is V x equals 1/2 k x square, it is the same for the negative x's and the positive x's. So, this is a symmetric potential. Any potential that has exactly the same value on two sides of the y axis is a symmetric potential, and it is not confined to potential being only positive. So, let me just write some more examples. So, I am talking about symmetric potentials. For example, I could write this potential, which is again the same on two sides of the y axis. This is also V x equals V minus x. This is also a symmetric potential. And why I am focusing on these right now is that they have a special advantage, they provide a special advantage while solving the Schrodinger equation. Let me look at the Schrodinger equation for such potentials. So, the Schrodinger equation is this plus V x psi x equals E psi x, and let me write this only for x greater than 0. The equation for x less than 0 is therefore going to be, from this equation, minus h cross square over 2 m d2 psi minus x over d minus x square plus v minus x psi minus x equals E psi minus x. All I have done is change x to minus x. Now, keep in mind that minus x square is same as x. Substitute minus x equals y, then the equation becomes minus h cross square over 2 m d2 psi y over dy square plus v y psi y equals E y. So, this is basically going back and forth. Important thing now is going to be that when I take this equation minus h cross square over 2 m d2 psi dx square plus Vx psi x equals E psi x and change to the other side of the y axis. So, that is some potential is there, and instead of writing here I want to write the equation for the other side. This is going to be minus h cross square by over 2 m. I can just change signs, psi x with a minus sign here over d minus x square plus v minus x psi minus x equals E psi minus x. This is same as Vx. So, since V is the same on both sides, the solution of the equation cannot be different, right. Vx and V minus x are one and the same thing, they give you exactly the same number as a function of. So, as a function of minus x, V gives you exactly the same number as a function of x. So, solutions cannot be different, at best they can differ by a constant. So, psi minus x is going to be plus or minus psi x. I choose that constant to be 1. Even if I take it to some constant c, I can always take that to be 1. Multiply by a constant does not really change the solution. The important thing is that if v minus x and Vx are the same, then the way solution evolves as a function of x on the right hand side. So, let me show this in black. The way the solution would evolve from a boundary condition say at 0 to the right hand side would evolve exactly in the same way on the left hand side, and therefore, the two solutions are going to be changed by only by a factor of plus or minus 1. So, this is an important property of the wave function for symmetric potentials, which I am going to make use of. So, in solving the Schrodinger equation, let me take the first example of particle in a delta function potential. And what I mean by that is that the potential Vx is equal to minus V0 delta of x. How does this potential look? This potential is going to look like this. If this is the x axis, this is the y axis, it is going to be very deep at x equal to 0, in fact going to minus infinity and 0 everywhere else. This could be a representation of a potential which is very deep and has very small width. Classically, whether this can afford a bound state or not, we do not know, but quantum mechanically I am going to show you that this affords a bound state. So, there is a bound state for this potential. What do we mean by bound state? That means the total energy E is going to be less than 0. The particle is going to be bound near the delta function. Let us see how does that come about. So, the Schrodinger equation for this is minus h cross square over 2 m d2 psi over dx square minus V 0 delta x psi x equals E psi x. And what that means is that if x is not equal to 0, then I have minus h cross square over 2 m d 2 psi over d x square is equal to E psi x, and this means minus modulus of E psi x, because E is less than 0. And what will happen at x equal to 0? I will show you in a minute. So, for x not equal to 0, I have minus h cross square over 2 m psi, let me write it as double prime for the second derivative, x equals minus modulus of E psi, and therefore, psi double prime minus 2 m E over h cross square, this is modulus, psi equals 0. This is a positive quantity, and therefore, you can immediately write the solutions. Psi x is going to be e raised to square root of 2 m mod E over h cross square x, or e raised to minus square root of 2 m mod E over h cross square x. That is the solution. Since this is a bound state, right, let me make the potential again, so that it is in our mind what we are solving for. The potential is right here, very deep, minus infinity. This is V naught delta x and 0 everywhere else. Since psi x represents bound state, that means the wave function psi x must go to 0 as x goes to plus or minus infinity. That means there is a almost 0 probability of finding the particle far away from the potential, and this immediately implies that psi x for x less than 0 is going to be e raised to square root of 2 m mod E over h cross square x with some constant a in front, and psi x greater than 0 is going to be some constant b e raised to minus square root of 2 m mod E over h cross square x. I have deliberately chosen these constants to be different because I do want to make a point. So, in this case that we are considering a delta potential V naught delta x potential, the solutions are psi x less than 0 equals some constant a e raised to square root of 2 m mod E over h cross square x, and psi x greater than 0 is equal to some constant b e raised to minus square root of 2 m mod E over h cross square x. What about boundary conditions? Psi x tending to plus or minus infinity is equal to 0 is automatically satisfied. Now, we have written the solution for x greater than 0 and x equals 0. What about at x equal to 0? This is the question. Recall what we asked or what we demanded from the solution of the Schrodinger equation. 1, psi x be continuous, and this means at x equals 0 the value should be the same from both sides. Now, if you look at the solutions, psi x equal to 0, if you come from the left hand side, that is x less than 0, this is a, and psi x equals 0 is b if I come from the right hand side. So, I will to denote that I will write the upper one as 0 minus 0 plus, and the two should be the same, and this implies a equals b. Number 2, we had demanded that psi prime x, that is the derivative of psi with respect to x, be continuous for finite potentials. Now, in this case, the particular case that we are dealing with, the potential is not finite at x equals 0, it goes to minus infinity. Therefore, this condition has to be replaced by some other condition, and we will do that now. So, the second condition, which is psi prime be continuous, is going to be replaced by something else, and let us see how that is replaced. We have the Schrodinger equation del 2 psi over dx square minus v 0 delta x psi x equals E psi x. Since the discontinuity is at x equals 0, let me integrate this equation with respect to x from 0 minus to 0 plus. What does that mean pictorially? If this is the potential minus v 0 delta x, I am integrating from slightly left from it to slightly right. I am integrating in this interval shown by green here. That means it includes the delta function, and keep in mind that integration of delta x dx from 0 minus to 0 plus is 1. Any function f x delta x integrated over from 0 minus to 0 plus is equal to f at 0. So, therefore, what do I get from this equation? Minus h cross square over 2 m. When d 2 psi over dx square is integrated, I get psi d psi by dx, and this is from 0 minus to 0 plus minus v 0 psi 0 is equal to E, some small interval which I can write as 0 plus minus 0 minus psi at 0. As the interval is made smaller and smaller, the right hand side is going to go to 0. So, the only conclusion I can draw now is that minus h cross square over 2 m psi prime at 0 plus minus psi prime at 0 minus is equal to v naught psi at 0. So, this is what the delta function does. If the delta function was not there, psi prime would have been continuous, but because of the delta function there is a discontinuity in psi prime, and that is what leads to now the energy. So, let us write this now. So, the boundary condition at 0 is now minus h cross square over 2 m psi prime at 0 plus minus psi prime at 0 minus is equal to v 0 psi at 0. Now, psi at x greater than 0 is nothing but e raised to minus square root of 2 m mod e over h cross square x, and therefore, there is a factor a also. Psi prime for x greater than 0 is equal to minus a times square root of 2 m mod e over h cross square e raised to minus square root of 2 m mod e over h cross square x, and psi x less than 0 is a e raised to plus square root of 2 m mod e over h cross square x, and psi prime for x less than 0 is going to be equal to plus square root of 2 m mod e over h cross square a e raised to square root of 2 m mod e over h cross square x. So, this immediately implies that psi prime 0 plus is equal to minus a square root of 2 m mod e over h cross square. The lower side immediately implies that psi prime 0 minus is equal to a square root of 2 m mod e over h cross square, and psi 0 of course a. So, if I substitute this in the equation above, the blue equation, I get minus h cross square over 2 m times minus 2 square root of 2 m mod e over h cross square is equal to V 0 times a. There is an a also floating around here, and we cancel this a, and I get 2 m mod e over h cross square is equal to m V 0 over h cross square. This 2 also cancels. So, this is equal to m square V 0 square over h cross raised to 4. So, what I have is from the boundary condition 2 m mod e over h cross square is equal to m square V 0 square over h cross raised to 4. We can again cancel some terms. This gives me h cross square, 1 m cancels, and therefore, I get mod of E equals m V 0 square over 2 h cross square, or energy E, which is equal to minus mod E, is equal to minus m V 0 square over 2 h cross square. How does the wave function look? The wave function, if I plot it along the x axis, is exponentially decaying on the right hand side, exponentially decaying on the left hand side. D psi by dx is discontinuous at x equals 0, and the energy E equals minus m V 0 square over 2 h cross square. That is the solution for a particle moving in a delta function potential. You can see it is bound, and it has energy which is slightly negative, and that is why it is bound, and the wave function is exponentially decaying on the two sides. There are no other bound states in this potential. So, this is the answer for this. If you want to normalize the wave function, right. So, let us see. Now, we have calculated the wave function psi x. Let me write it in 1 bracket e raised to minus square root of 2 m mod e we have calculated over h cross square x for x greater than 0, a e raised to square root of 2 m mod e over h cross square x for x less than 0. A is yet not fixed. If you want to fix it, what we will do is we will take psi x square, integrate it from minus infinity to infinity, which will give me some a square times some constant, and fix it equal to 1, and this will normalize the wave function and give the total probability of finding particle anywhere in the interval x minus infinity to infinity to be equal to 1. Then I will have a normalized wave function. So, this is a very simple problem to start with. The way I would generalize this would be 2. So, let me take example 2. So, the way to generalize this will be 2 delta functions So, in this case I have the x axis, this is x equals 0, and to make the problem simple, what I will do is I will put the delta function symmetrically about x equals 0, and both are the same, V naught delta x minus a, and this will be minus V 0 delta x plus a. So, again the potential is symmetric, V minus x equals V plus x, and therefore, the solution is going to be either symmetric or antisymmetric. In this case, it so happens that we get two bound states, and let me show you how. So, the Schrodinger equation is h cross over 2 m d 2 psi over d x square minus V 0 delta x plus a psi minus V 0 delta x minus a psi equals E psi. For x not equal to a or x not equal to minus a together, the equation is minus h cross square over 2 m psi equals E or psi double prime psi, which is minus modulus of E psi. So, the equation I am solving again is h cross square over 2 m psi double prime is equal to minus mod E psi or psi double prime minus 2 m mod E over h cross square psi equal to 0. So, the solutions again are e raised to 2 m mod E over h cross square root x, or e raised to minus square root of 2 m mod E over h cross square x, or a linear combination of the two. Now, let me show you how you form this linear combination. Even if you do an elaborate exercise, you will get exactly the same answer. So, here is my x axis, the potential is symmetric, minus V naught delta x plus a minus V naught delta x minus a. So, I know that on the right hand side the solution has to decay. I am going to plot the wave function on the upper side. These are the potentials, minus V naught delta x plus a minus V naught delta x minus a, and on the right side the potential has to decay exponentially, e raised to minus square root of 2 m mod E over h cross square x. So, on the x positive side the solution has negative power of the exponential. On the left hand side the solution again has to decay because it is a bound state. In between I am going to have either symmetric or antisymmetric solutions. So, symmetric solution would be a linear combination of the two, and let me show on the lower side the antisymmetric solution, and that would be the solution decaying on one side. Then antisymmetric solution has to go to 0 necessarily through 0, it has to be 0 at the 0, and again exponential on the other side. So, this is e raised to minus square root of 2 m mod E over h cross square x. This is e raised to square root of 2 m mod E over h cross square x, and in between it is an antisymmetric combination. Symmetric combination is going to be e raised to this square root whole thing plus e raised to minus square root of the whole thing, which is nothing but the hyperbolic cosine function. X, and the lower case this is going to be an antisymmetric combination. So, it is going to be e raised to square root of this whole thing minus e raised to minus square root of this whole thing, and this is going to be sine hyperbolic of 2 m mod E over h cross square root of x. So, I have given you a qualitative argument based on symmetry, how the wave function should look like, as to what the linear combinations of these two solutions would be for the symmetric and antisymmetric wave function. So, in the first case psi x equals psi minus x, and the second case psi x equals minus psi minus x. This is a qualitative argument based on the symmetry. If you want to do it mathematically, what you would say is psi x is equal to a e raised to minus square root of 2 m mod E over h cross square x for x greater than a. Psi x is equal to some constant b e raised to minus square root of whatever this quantity is plus c e raised to plus square root of this whole thing x for x between a and minus a, and psi x equals some d e raised to square root of 2 m mod E over h cross square x for x less than minus a, and then match the boundary conditions that the psi be continuous at the boundary and so on, and then you will find your solution. Now, this I will be assigning you as an assignment problem to find the energy and eigenfunctions. Actually, eigenfunctions I have already written for a particle moving in a double delta function potential. Significance of this problem is that a single delta function is like an atom and a double delta function is like a molecule. And in this case, you would find that symmetric psi has energy lower than the atom, so that is why molecules get formed, and antisymmetric psi has energy greater than the atom, and as a tends to infinity, both energies become equal to that of the atom. So, let me conclude this lecture by stating that we have looked at the nature of psi x for V x equals V minus x potentials. 2, we have solved the Schrodinger equation for a particle moving in a delta function potential. And third, we have half solved, and I will give you rest as the assignment for a particle moving in a double delta function potential.